Buenas tardes, bienvenidos a esta nueva conferencia del ciclo La ciencia en el cosmos, la ciencia del cosmos, que organiza la Fundación BBVA. En esta ocasión tengo el placer de presentarles al profesor McCaughrean. Marc trabaja actualmente en el Directorado de Ciencia de la Agencia Espacial Europea. Solo decir que este directorado es el que coordina, el que realiza la mayoría de las misiones científicas de la Agencia Espacial Europea, de muchas de las cuales nos va a hablar hoy. Y Marc lleva 8 años, 7 años, trabajando en la Agencia Espacial Europea como asesor dentro del programa científico y además se encarga de comunicación, difusión, divulgación de los resultados científicos que obtiene la agencia para todo el público en general. O sea, es una persona encantadora, le encanta hablar con la gente, presentar los resultados, además lo hace muy bien. Nosotros en el comité del programa científico esperamos con impaciencia a todos los delegados a que llegue la presentación de Marc, donde nos cuenta los resultados de los últimos meses, y es el momento más tranquilo, más relajado y más placentero de las reuniones del comité, que por otra parte son más duras. Aparte de divulgador, Marc tiene un excelente currículum científico, sacó su tesis doctoral en la Universidad de Edimburgo y después se ha estado moviendo por distintos centros de investigación y universidades en Estados Unidos y en Europa, hasta recalar en la ESA hace unos años. Su campo de especialización en ciencia es la formación de estrellas de sistemas planetarios. Hoy, en principio, nos iba a hablar del sistema solar, pero haciendo la presentación no ha podido reprimirse y va a ir algo más allá del sistema solar, hasta por lo menos toda la galaxia, y no sé hasta dónde más, pero ya nos contará. Entre otras cosas, es científico multidisciplinar del telescopio espacial James Webb, que se lanzará dentro de 2 años y será la joya de la corona a nivel mundial. Es un proyecto común entre NASA, ESA y la agencia canadiense. Y es un telescopio destinado a estudiar la frontera del conocimiento, la frontera del universo. Si todo va bien, será un excelente proyecto y Marc trabajará en él como científico pluridisciplinar. No digo nada más, simplemente disfrutar de la conferencia, preparad todas las cuestiones que podéis tener acerca del sistema solar, de la galaxia o de lo que se os ocurra, que Marc seguro que os las contesta amablemente después. Y adelante.
Thank you very much, Miguel. Muchas gracias. And thank you to the Foundation for inviting me this evening to talk to you. I'm afraid I will have to do it in English, so if you need to put your headphones on, now is a good time. And I'm going to do it in English because I have a lot to talk about, and so I'm going to get the simultaneous translator really going at high speed because I'm going to speak fast. There's a lot to talk about. In fact, you'll see the change of title. The original title was about the solar system, but I decided there's so much happening in ESA's science program at the moment that I would make it a little bit bigger than that. So what I'm going to talk to you about is our science program and the missions which we're currently flying, and the ones we're going to be building and flying soon. And I'm going to come at the second half of the talk to talk about the solar system. So what you see here are the missions in the solar system which are currently operating, flying, for example, at Mars. We have the Mars Express mission. We are sharing in a mission which is at Saturn, the Cassini mission with NASA. We have missions looking at the Sun, the SOHO mission. And we also have missions which are actually close to the Earth, measuring the magnetic field of the Earth and how the Sun, the wind of the Sun, interacts with the Earth's magnetic field. And of course, one thing I'm sure you're interested and keen to hear about, let's see if I can get this to work, is this one here, the Rosetta mission, which everybody I hope is familiar with, our famous comet chasing mission. And I will finish with that at the end, because of course next week is an incredibly big day for us in ESA. That's when we end the Rosetta mission after 12.5 years in space. And it's going to be, I want to leave it to the end because I typically get quite emotional and start crying at the end. And I want to leave that for the end. I want to be a grown-up before I get to the very end. And I'm also going to talk to you about ExoMars, which is a mission on the way to the red planet right now. And in fact, after we finish with Rosetta next week, just 2 weeks later, we're going to land on Mars as well. So we have a lot going on. Now, we also have a lot of missions which are astronomy missions. Much of the universe is so far away, you can't actually go there with your spacecraft. You have to study it from here. And we have a whole range of missions which look at far infrared wavelengths, very cold material in the universe, the Planck and the Herschel missions on this side. They're not actually operating anymore. They ran out of their coolant, but they're still producing a huge amount of science. And then we have, of course, the Hubble Space Telescope that you all know of. And we have missions here, Integral and XMM, which are high-energy missions, which study the most extreme, violent places in the universe. As material, for example, falls into a black hole, it heats up and gives off X-rays. I'm going to talk to you about Gaia, which is something we talked about a lot last week in the press, because we had a press conference here at ESAC, our science operations center, just 20 kilometers away from Madrid, because we released a huge amount of data from that mission for the first time for the world to play with. And I'll tell you what we did and what those data are. Now, there's one thing where you can see at the top, and Miguel already talked about it, and this is the James Webb Space Telescope. So this is, if you like, my mission. 10 billion euro mission. It's all mine, all mine. Now, I've been working on it for 20 years, and it comes from my scientific interest, which is personally looking at stars and planets being born around stars a long way from here. New stars, baby stars. And for that, you need, to make the next big step scientifically, you need this telescope. Now, for a very long time, this telescope has looked like this. PowerPoint, just a picture. But it is a real machine. We started putting it together in 1996, and in 2 years' time, we're going to launch it. This is a NASA-led project, but it has very strong European participation, because Europe has built 2 out of the 4 instruments. Half of the instruments are European, and we will use our Ariane 5 rocket from French Guiana to put it into space. And for NASA to trust Europe to launch their big observatory is a big statement of faith in what we're able to do, so we're very proud of that. But it's a very real telescope. So the next thing I'm going to show you is the real telescope. And during this talk this evening, I'm going to use music, and I'm going to show you videos. And this first video shows you James Webb a few months ago as it was being put together in the United States. So that amazing machine has a main mirror 6.5 meters across. That's much too big to put into space. That's why it will be folded up, put on the top of a rocket and sent into space. And then in space, it will unfold like a flower blossoming. And we hope it all goes right, because if it doesn't, it's so far away from the Earth, we won't be able to go and fix it. So that's why we're spending so much money to get it right, and why it's taken so long to get the engineering right. These things are very tricky indeed. Now, I'm going to jump back to an observatory which we did launch in 2013, and that's the Gaia Observatory. Now, Gaia looks very different. It doesn't have a big mirror to collect the light. Those mirrors are actually inside, and I'm going to show you a little bit about that in a moment, how it was made and how it works. But what's the problem? What's the issue? What are we trying to solve with Gaia? What we're interested in is the Milky Way, the band of light which covers the night sky, which you see here. This is taken in the Alps near Innsbruck. That band of light you can see on a dark night is the galaxy we live in, a collection of 100 or 200 billion stars. And we live in that galaxy, and because we live in it, we can look towards the center and see the light of the stars, but we can't really see it properly because we're inside it. What we can do is take a picture of another galaxy like this. This is the Andromeda galaxy, which is very similar to our galaxy. And now you can see the old stars in the middle, the old red stars, the new young stars being born in the spiral arms. And in our galaxy, we live somewhere near the edge, looking towards the center. What you also see in this image, though, is another galaxy here. And this is very important, because this tells us a story about how galaxies are made. Galaxies form over the history of the universe, roughly 14 billion years. But they don't just form on their own. They form out of smaller galaxies. Big collections of stars fall towards each other under gravity and build up the big galaxies. And that would look something like this. So this is a simulation of how a big galaxy would form, a computer model. And you can see small galaxies falling in and their stars building up the big galaxy. But you can also see that there are some trails and shells as these galaxies fall in. And that tells us that when the galaxies collide, they don't hit each other. The stars are too small, and they live very far from each other. So when galaxies fall towards each other, the stars do not hit. They don't explode. They pass through each other and then come back together. And the motions of the stars tell you something about how the galaxy was put together in the first place. So if you want to understand the history of the way a galaxy like ours was made, you want to measure a three-dimensional movie of the Milky Way. You want to measure the positions of the stars and their movements. If you can do that, you can make a movie. You can play it forwards to say how the Milky Way will be in the future, or you can play it backwards to see how the Milky Way was put together. So how do you do that? Well, you've got to start by measuring the simple parameters. The first one is the position on the sky. I look up at the sky, and I see a star, and it's there. What I don't know is how far away it is. Now, if all stars were the same, all stars had exactly the same brightness, then if a star, when I see it, if it's very dim, it must be far away. If it's very bright, it must be close. But unfortunately, that's not how stars are. We have very different brightnesses of stars, and we can't tell just by looking at it how far away it is. But we can measure it. And we do it like this. So Gaia is in the solar system next to the Earth, and it goes around the sun with the Earth. So let's imagine this is March, and we take a picture of this star, and we see where it appears against the background. So if these are all the very distant stars, then this nearby star will appear there. Now, if 3 months later we do the same measurement, it will have moved against the background. And we do that again. It's moved again. 3 months later, and so on. So in 1 year, that nearby star will make a little ellipse on the sky. If it's above the solar system, it will make a circle. If it's in the same plane as the solar system, it makes a line. And anywhere in between, it makes an ellipse. Now, here's the interesting thing. We know that distance very accurately. And if we can measure that angle, how much it moves, how big the circle is, then we can work out how far away the star is. So this is a very simple technique for working out the distances to stars. It's called parallax. And you can do the same thing right now. So if you all hold your thumb up, if you would hold your thumb up, I will have to wait for the translation. Now, hold it close to your face and close one eye. Now close the other eye. And you will see your thumb move backwards and forwards. Now put your thumb as far away from you as you can and do it again. It only moves a little bit this time. So that's how you measure the distance, simply from that amount of movement. So what Gaia does is measures the positions of all of the stars and how they change during the year. Which brings me to this diagram, which is my favorite plot I've ever made in my life. I've given maybe 1,000 talks in my life, And this is my favorite plot ever. Because if you want to just make a cartoon of it, this is what the stars do. If I say these are the nearby stars, these are the middle distance, and these are the far distance, then what happens is this. That's why it's my favorite slide. And I actually like it so much, I always show it twice. So that's what you measure. You measure those little circles during the year, and then you can tell the distances. But it's not that simple, because the stars are also moving. They're also doing that. So during the year, we measure the circle plus the motion of the star. We might see it do that, we might see it do that, and we have to measure all of this extremely accurately to work out the distances and then the movements of the stars. What do I mean by accurately? How accurately do I have to do this? Well, with your experiment here, it was quite easy to see your thumb moving. But Gaia, the most distant stars it can measure positions for, the movement they make in 1 year is the same as the width of a human hair at 2,000 kilometers. So we can measure with this machine the width of a human hair at 2,000 kilometers away. And that means, of course, we want to be away from the Earth in space to make this measurement where everything's very stable, there's no atmosphere in the way. We want the best place possible. That's where we go into space. Now, if you've been following, you will realize that I have left one thing out. Because what we've measured so far is position X, position Y, and the distance. So I now have 3 dimensions. I've also measured the movements in X and Y, but I haven't told you how I've measured the movements this way. That's a different thing. So actually, we use a completely different instrument on Gaia to do that, and we measure the spectrum. We split the light of the star with a prism, and then we look in this little piece here of the spectrum in the red, and we see there's a dark line in all kinds of stars. These are very hot stars and very cool stars, and all stars have this dark line, and that's because they have calcium in their atmospheres, and when the starlight from underneath goes through the cool atmosphere, the calcium absorbs a little bit of light and leaves that black line. So we can measure that black line, and we can look to see if it's where it's supposed to be, at the right wavelength, or if it's moved slightly to the red, then that means the object's moving away from us. What's what we call redshift. It's the same as Doppler shift. When objects move away from you, the frequency of sound, if it's an ambulance driving away from you, or if it's a star, the frequency of light gets redder, and if it moves towards you, it gets bluer. So we measure that slight movement, and we can measure the speeds of the stars, and that tells us, now we have 6 dimensions. So that's what Gaia is doing for 1 billion stars in the Milky Way. And this is how Gaia looks. It's 3 meters across here, has 2 separate telescopes looking at different locations on the sky at the same time, and then it scans around the sky and measures the positions of the stars there and the positions of the stars there, keeps going around. Here are the 2 telescopes again. All of the light from these 2 telescopes comes down here. This is the camera, and both telescopes put their pictures on the same camera, and there it is. It's the biggest camera ever put in space. It has 1 billion pixels. Compare that to your mobile phone, which might have 10 or 20 megapixels. This has 1 gigapixel. And in fact, it's so big, we can't download images. We can't download all of that data. It's too far away from the Earth. The amount of data is too big. So all we download are the positions of the stars. As they go past, we say, where is the star? And send the coordinates back. So we never take pictures, or very rarely take pictures. So that's what Gaia looks like. The 2 telescopes, this is the back of the camera, and then we have this big sun shield which shields the telescope from the heat of the sun to make it very stable so that it doesn't move inside as it's rotating around. So you fold that up like this, and you put it on top of a rocket, in this case, a Soyuz. launched from French Guiana, and you put it into space. And then when Gaia arrived in space, it's doing this. Since 2013, it has been scanning, rotating every 6 hours, scanning out stars in the Milky Way, sending the positions down to Earth repeatedly, all the time, constantly. It never does anything else. This is what it does. So it's an incredibly boring mission when it comes to where it looks. But the data are amazingly exciting because we are beginning now to build this movie of the Milky Way. And just last week, we released the first image of the sky. Now, I told you Gaia doesn't take pictures. It just measures where the stars are and sends the coordinates. So what this image is a plot of how many stars there are in each pixel across the whole sky. How many stars are there? If there's lots, it's bright. If it's dark, it's faint. What you see is the Milky Way here. These are all the dark clouds with gas and dust absorbing the light from beyond, and we see the clouds. You also see these patterns, which are actually, that's from Gaia. Gaia has not finished its full map of the Milky Way yet. So it's taken nearly 500 billion measurements in the last 3 years, 500 billion measurements. But even then, we don't have the complete map. It will take us for a full 5 years to get the full data set. So what we released last week was the positions, the two-dimensional positions, not the distance, the two-dimensional positions and the brightnesses of 1 billion stars. It's the most accurate map ever made of our Milky Way already. We also released 2 million stars, which we know the distance to and their movements already. And that's 20 times more than anybody has ever had before. So when we pushed the button last week to open the archives, the first scientific papers were written in less than 12 hours. People had been waiting for years for this. Some people had written 3 different papers saying, if it turns out to be green, I'll submit the green paper. If it turns out to be red, I submit the red paper. They then spent 1 hour reducing the data. Oh, it's blue, we'll send the blue paper. So they were prepared, and we have lots of papers already arriving from Gaia. And next year, at the end of next year, we will release the full 6-dimensional map, all the movements in 3 dimensions, the positions in 3 dimensions and the movements as well. And when I say release, they're free. You can take them. You can download these data. It's not for scientists only. Anybody in the world can take these data. Completely free. I don't know what you're going to do with it, but please be my guest. If nothing else, you can make some pretty pictures out of it. But no, there's a lot there. So, Gaia has been operating, but I want to talk to you a little bit about risk, because space, it can be very nice when you get, the launch is very dangerous, of course, but once you get into space, you think it's quite calm, nothing happens. Well, sometimes things happen, and Gaia had an interesting event last year, in August last year. It got hit. It got hit by something in space which caused it to spin up, to get faster. It rotates very precisely every 6 hours, and it rotates, we make sure it rotates at the same speed by using atomic clocks on board. It has to be incredibly precise. But if something hits it, it knocks it. And that's what you see here. This is the torque on the satellite suddenly increasing for a few hundred seconds. So something hit the satellite and changed its speed. We then corrected. We used the atomic clocks to make it go the right speed again. We also measured the amount of energy that this thing hit the satellite with. We could do that because we just measured the whole satellite warm up by 0.2 of a degree, 0.2 degrees centigrade, and then it cooled down again over 20 hours. So we know how much the satellite weighs, and if it heats up by 0.2 degrees, we can work out the energy that must have been deposited in the satellite. And the answer is 84 joules. I know that doesn't mean anything, but I'll explain what that means in a minute. 84 joules. Now, here's the interesting thing. You probably remember from school or maybe university that this quantity called kinetic energy is 1/2 times the mass times the velocity squared. 1/2 mv squared is the kinetic energy of an object. So we know the energy equals 1/2 mv squared. But we know velocity as well, because this happened in August last year. And in August, every year, the Earth passes through the tail of a comet. And we get meteorites, a meteorite shower. It's called the Perseid meteorites. And because we know where they come from, we know we can measure their speed. We've been measuring them for a long time. They come past the Earth at 59 kilometers per second, which is fast. So now we know the amount of energy, we know the speed, we can work out the mass. And the mass of this object is 48 micrograms, 48 millionths of a gram, which is the mass of an eyelash. So this thing hit our spacecraft, just something tiny, a little speck of dust with the mass of an eyelash, and slowed us down, heated us up. 84 joules. How much is 84 joules anyway? Well, 84 joules is the same amount of energy that a rugby ball has passed at full speed. An eyelash with the same energy as a rugby ball thrown at our spacecraft. So this stuff happens in space, even though you think it's quite clean out there. Even little specks of dust can cause our satellites problems. Gaia was not injured by this. It's designed to survive this. But again, a little bit of an expression about what happens in space. I talked about this material coming from the tail of a comet. Well, we occasionally do take pictures of comets in space, of objects in space, and we did take a picture last year with Gaia right there. And this is one of the most famous comets in the solar system. It's comet 67P Churyumov-Gerasimenko. It's the comet that Rosetta is flying around. So right in the middle, brightest dot there is Rosetta as well. So that's kind of cute, one of our spacecraft taking a picture of another one, even if you can't quite see it. And I'll come back to Rosetta right at the end. So let's change completely now. Let's change to a totally different topic and to a mission called LISA Pathfinder. Now, LISA Pathfinder was launched at the end of 2015, so less than a year ago. And here's the satellite, and behind it is just the propellant module, the propulsion module, which took it to its home. And the weird thing about LISA Pathfinder is that its entire job is to measure nothing, and to measure nothing as accurately as possible. Okay, I better explain. What we're actually interested with LISA Pathfinder is it's a technology mission exploring the technologies for measuring gravitational waves. Now, gravitational waves have been in the news, but let me give you an idea what they are. So gravitational waves are what we call ripples in space-time. Now, you all think about space, we fly in space, but actually, if you think, when you talk to Einstein or read his books, there is no such thing as space. There's a thing called space-time. Space and time are linked, and we call it space-time. And space-time is that, and it's that, and it's inside me, it's everywhere. Space-time is the fabric of the universe. It's not the air, it's not the vacuum, it's the grid, the structure on which the whole universe is built. And what Einstein predicted is that gravity can't move at the speed of light, nothing, or beyond the speed of light, it can't be instantaneous. So gravity must move at the speed of light. So when I move closer to somebody in the front row, we exchange signals through gravity. Because I'm now closer, the gravity is stronger between us. If I move away again, so something has to send that signal with gravity, and that's what gravitational waves are. They're sending a signal through space-time saying, oh, mass is moving, and those signals move at the speed of light. And the way you would see it is by space-time changing its shape. But it changes by an incredibly small amount, because space-time is the stiffest thing you will ever come across. It feels you could do, but that's not space-time. Space-time is there and it's rigid. So when gravitational waves pass through space-time, they make it change its shape very slightly. And the way it does it is not when we move closer to each other, it doesn't send ripples this way, it sends ripples sideways, if you like, what we call transverse waves. And so we want to measure that to see gravitational waves in the universe. Now, you could ask, why are gravitational waves interesting? Okay. Why would you actually want to look at gravitational waves? I've got all these wonderful optical telescopes like Hubble and XMM and Integral. Why do I care about gravitational waves? Well, imagine that you were standing in a forest or in a jungle and it looked like this. Now, you see some trees, you see some leaves, you see some bamboo, you're learning something, you're actually looking at the data. There's a waterfall. Well, okay, I'm learning something there. Now imagine I turn on a different carrier of information. So all of a sudden, you know much more about that forest because there's another signal that's coming through sound, not through light. And the same is true of gravitational waves. They come from places we can't see with our telescopes. So for example, black holes, when black holes merge together, black holes are black. We can't see black holes. The gravity's so strong, light can't escape, but gravitational waves can. And so if we can measure gravitational waves, we can understand what happens when black holes join together. So, of course, only a year ago, after years and years of looking, the very first detection was ever made of gravitational waves, and it was made by an experiment called Advanced LIGO. And what you have here are two tubes with a vacuum inside at 4 kilometers long. In here you have powerful lasers which go all the way down the tube, hit a mirror, and come back again, and you do it simultaneously down both tubes, and when the light comes back, if nothing has changed, the light will arrive back at exactly the same time because they're exactly the same length. But if a gravitational wave comes through at the moment you're taking an observation, it will change the length of one of the arms compared to the other one, and the signals will come back out of phase. They won't come back together exactly the same time. And in September last year, this machine detected the first ever gravitational waves. And I'm going to play you the sound of those waves. I'm going to play it first at the normal tone and then just lift the tone up so you can hear it a bit more clearly. Now, the reason you see two traces there, they actually have two of these machines. They're in the United States, but it's a big international project involving Europe as well. And if you see the same signal in the two machines at pretty much the same time, separated only by the speed of light between those two places, it must be a real thing. So this is a way of getting rid of false signals. That 0.2 of a second signal right there is the sound or the signal of gravitational waves from two black holes, each one 30 times bigger than the sun, or 30 times the mass of the sun, joining together in just 0.2 of a second. And they gave out, as they collapsed together, they gave out this blip of energy which was captured on the Earth nearly 1 billion years later. And that's what that is, and that's a Nobel Prize right there for those 0.2 of a second. Nobody is taking any bets on the winners of Nobel Prize in physics this year because we all know who's going to win. We don't actually know, but we're pretty sure. So that's an amazing detection. And then you would say, well, okay, you've done it. Who cares now? Why do you want to do it in space? Well, because for the same reason we go into space to look at different wavelengths of light. Visible light we can see from the ground, but the Earth's atmosphere absorbs X-ray light and very long wavelength light. So we need to go into space to measure those things. For the same reason, if you build a gravitational wave observatory on the ground, then you can see frequencies, signals at about 100 times a second, 100 hertz, and those are typically quite small objects merging together quickly. If you want to look at really big objects, the centers of galaxies joining together with billions or millions of solar masses, that will all happen at much lower frequencies because it's much slower. And then you need to put the machine into space to do it. So we're doing science if we can go into space, which is different from what you can do on the ground. So how do you do this? How do you do this in space? Well, sorry, I'm At some point, I'm going to rotate this so I can see my next slide, but that's why I keep walking over here. So what sorts of things then can you detect in space? Well, I talked about big black holes, and the first one that you would look for are these giant black holes in the centers of galaxies. Remember I talked about Gaia and the way that galaxies are made by putting small galaxies together? Many galaxies have black holes in the middle. So when those galaxies join together, the black holes will merge, and you will see something like this. In the center, these giant objects spiraling together, and as they do, they get closer, they give out gravitational waves. And we can measure that. You also have places where you have big objects and little objects falling in, and we can watch those as well. And those are kind of interesting because they create the following sound. And that's what happens at the end. When the little object falls in, it suddenly stops. So it's that vroom, beep. And that's what we listen out for with our gravitational observatories. So how do we do that? Well, what you need to do to measure very slow frequency gravitational waves, you need to measure them over a much bigger distance. LIGO is just 4 kilometers. We need to measure over a much bigger distance. 1,000,000 kilometers. We need to send our lasers 1,000,000 kilometers one way and that way, and then bring the signals back. And you can't do that on the Earth, obviously. The Earth isn't that big. So you can do it in space. You can put 3 spacecraft out there in space and send lasers from one to those 2 and back again. And you do it by big telescopes, sending the lasers to one satellite, effectively bouncing it off a mirror and sending it back again. And the mirror, in this case, is right in the back here, and I'm going to show you what that looks like in a moment. It'd be a little cube made out of gold. And so what we've done to test this, instead of having these 2 spacecraft 1,000,000 kilometers apart, we've put them inside one spacecraft 38 centimeters apart to test whether we can make this experiment work in space, the technology part. Because what we have to do is we have to make sure that when we're looking for gravitational waves, that there's nothing else moving the mirrors. There's no light from the sun, cosmic rays, meteorites, nothing else is moving the mirrors. Because if the mirrors move at all, due to any other signal, we will never measure the gravitational waves. And I want to give you a sense of what we have to measure. We have to be able to measure the movement of objects to 1 picometer. That's 1/1,000,000th of a millionth of a meter. So that's the same as the width of a human hair around the whole planet, 40,000 kilometers. And so you have to keep the entire system incredibly still. You have to find a way of making sure the mirrors, these cubes, are completely still. And so what we've done is we've put them in one satellite and linked them with lasers. And then we put this into space and see if we can keep the machine quiet. And that's what it looks like inside. So we have these 2 little cubes, 38 centimeters apart, buried right in the middle of the satellite. And the whole job of the satellite is to avoid anything affecting the cubes, because the cubes are not touching the satellite at all. Once we get into space, we let go of them. They're just flying through space, not touched by the spacecraft. And the whole job of the spacecraft, if the spacecraft feels it's being moved towards the cubes by the light of the sun, you fire a little thruster and move away again. And if you get pushed this way, you move that way. The satellite's permanently moving around, never touching the cubes, providing the cubes a perfectly quiet place. And I'm going to hand out, just to give you, so you can get a feeling. The original ones are made of gold, and they weigh 2 kilos each. I never bring those to talks because they're going to get taken in airport security. I don't have gold ones anyway. I only have ones made of tungsten. So I will give those out just so you get a feeling. Hold them 38 centimeters apart, and your job is to make sure they don't move to 1 picometer. So, if you put it into space now, then again, just to tell that story. Oh, sorry, this is the launch of LISA Pathfinder because we're rocket scientists and we like to show launches. This is on a Vega rocket, smallest rocket in the European Space Agency, again from Kourou at the end of last year. And I see I have a friend on the soundboard who likes to turn my music down. We're not going to be friends by the end of the evening if you keep doing that. Anyway, so what we do is we're out here 1.5 million kilometers away from the Earth at this point, and here come the little cubes flying through space, 38 centimeters apart, linked by lasers to measure their distances, buried inside the spacecraft. The whole spacecraft is moving around. The cubes are not moving, the spacecraft's moving. And you'll see that the spacecraft moves under the influence of the sun, and we use these tiny little thrusters to keep the cubes from moving. We launched this in December last year, and it works. It works amazingly well. It's taken nearly 15 years to build this mission, and within weeks, it fully reached its requirements. It fully proved the technology. And here's the graph. It's very complicated, and I just want you to concentrate on two things. This is the amount, effectively the amount of movement, and this is the frequency. So we measure this movement at different frequencies in the spacecraft. This is what we needed to prove with LISA Pathfinder, and this is what we've measured. This is 30 times better than the requirement. So this system works so well, it's 30 times better than we need. And what that lets us now do, we have actually proven the technology to build the full machine now. We can put these satellites linked by lasers 1 million kilometers apart, fire the big lasers back and forth, and measure these cubes flying through space, and now measure real gravitational waves. Because LISA Pathfinder is too small to measure gravitational waves. We wanted to prove the technology. Now we can move them apart. And we still need to measure 1 picometer, 1 millionth of a meter, but now over 1 million kilometers. That's the same as measuring the width of a human hair at the distance to Epsilon Eridani, one of the nearest stars to the Earth. It's 10 parsecs away, 30 light years away. We will measure the width of a human hair, or the equivalent, at 30 light years. This is where astronomers like to talk big numbers. It means nothing, but I can assure you it's very, very accurate. So we are now ready to build this machine, and we will try to put that together. It will take time, and we expect maybe to launch it by around 2030. It's going to take a while. Okay, so that's LISA Pathfinder. Now it's time to move somewhere completely differently. It's time to move to Mars. Because, as I said in the beginning, on the 19th of October, we will be landing on the surface of Mars with a small technology demonstrator called Schiaparelli. But it's part of a bigger program, a two-mission program that may be extended between the European Space Agency and Roscosmos, the Russian space agency. NASA have a small piece of the mission as well, and we have these two satellites. The first one we've already launched, and I'm going to explain that. That's on its way. And this, a rover to drive on the surface of Mars, will be launched in 2020. So let's talk about the 2016 mission that was launched in March this year. It has two main components. This is the main satellite, which we call the Trace Gas Orbiter. I'm going to explain what that means in a minute. It has 4 instruments on board, camera, a neutron detector, and 2 very sensitive spectrometers which will measure very rare gases in the atmosphere of Mars. It also has the lander on the front, which will go down to the surface. It's to prove the technology, because Europe has never successfully landed on the surface of Mars before. And we need to prove we can do this. So this is not really the scientific part here. This is going to go to the surface, and 3 days later it's going to die. So don't expect to get attached to this lander. It will be dead after 3 days. But it is critical for us to prove we can get to the surface of Mars for our next mission in 2020. So, what is the Trace Gas Orbiter? Because this is really exciting. In 2003, we launched a mission called Mars Express. It went to Mars, and it's been operating. It's still operating today. And one of the first discoveries it made was methane in the Martian atmosphere. Nobody expected that. Not at all. Methane gets destroyed very quickly in the atmosphere by ultraviolet light. And so why is there any methane left on Mars? The only reason can be if the methane is being made every day, a new methane is being put into the atmosphere. Now, you think that's the detection of methane. It's not, it's that. So it was pretty uncertain. Lots of people doubted it. Lots of people said that couldn't be true. Better measurements since then have proven that it's really there, the methane. Why is it exciting? Because methane can really come from two places on Mars. One is geology. Somewhere deep under the surface of Mars, there will still be liquid water and warm liquid water. And in those places, rocks change from one kind into another, and one of the things that comes out is methane. So it could just be a sign of geology, but it could also be a sign of biology, because we have primitive life forms on the Earth that were the first life forms on the Earth. Before there was any oxygen in our atmosphere, there were things called methanogens. They're still here. They're in swamps. They're in your stomach, places where there's no oxygen, making methane. So, if there's methane on Mars, it could be geology, but it could be the sign of life. And we want to study that. We want to measure where the methane's coming out. We want to see if it depends on the season. Is it to do with temperature? Is it to do with life near the surface, getting warm in the summer, giving out methane? So we need to go and measure methane very accurately on Mars. So this is the spectrum from Mars Express. Now stretch it out. Now this is what the trace gas orbiter will start doing. These are what its measurements will look like starting beginning of next year. So now, this is methane. So we will be able to measure methane like this. We'll be able to measure water and other carbon molecules like ethane, hydrogen chloride. We'll be able to measure sulfur as well. And that's important, because if the methane comes out with sulfur at the same time, then that means it's probably geology due to the heating of volcanic activity under the planet's surface. But if it comes out with ethane, another carbon molecule, then it's more likely to do with life. So we're going to go and measure this and measure it extremely accurately in the next few years to try to map it. This is what the machine looks like. This is the big antenna pointing that will send all the data back to Earth. Here's the satellite. These are balloons to take the gravity from the antenna when it was being tested. Here's the big solar panel. There's a person there to give you a sense of scale. This is the trace gas orbiter, the lander being put on the top, and then put inside a proton rocket provided by Roscosmos. They put their stuff horizontally, and as you'll see in a moment, they go out horizontally and lift the rockets up. We put our stuff on vertically and drive out vertically. So I'm going to show you a movie which now shows you from this stage all the way through to launch. And again, with my musical tastes, we'll see if it gets loud enough. So we went 14th of March, we're on the way, and we arrive on 19th of October. And this is what the landing sequence of the lander will look like. We use parachute, a heat shield, parachutes, and then retro thrusters to slow us down just before we hit the surface. And here I can't resist. We haven't quite finished this animation yet, so it's not, you're seeing it before it's been released to the public fully. But this is what the landing will look like a completely different way.
The weather's
So you can see we turn the rockets off about 2 minutes above the surface and drop it. You know, why not? So again, it will last for 3 days, and it's very important because that will take us again towards the technology needed to put the rover on the surface in 2020. And the rover is doing something unique, never done before. It's going to drill 2 meters underground and pull material up and analyze it in a laboratory on board. And why 2 meters? Why do we want to get underground? Well, again, there's lots of ultraviolet light hitting Mars. It doesn't have a very thick atmosphere, it's a very thin atmosphere. And the surface of Mars is completely sterilized by ultraviolet radiation. So if there is life on Mars, it has to be at least a couple of meters under the surface. We don't completely expect to see life today. We hope to find signs of life in the past, leftover organic material. If we're really lucky, we might actually find something living 2 meters under the surface of Mars. So that's really exciting. So let me finish with the one you've been waiting for, something equally exciting, and that's the Rosetta mission. So Rosetta is this amazing mission to study a comet 67P. Oh, sorry. I came all this way, and if you want to know where we're going to land on Mars, then, so please pay attention. See if you can find Schiaparelli on the beach ball. It actually shows all the landers that have ever landed on the surface of Mars, so we're trying to be equal opportunities there. So, Rosetta. We're studying this comet, 67P Churyumov-Gerasimenko. Why? What's exciting about comets? Well, comets are these amazing objects that come into the solar system. Seemingly randomly, over history, people thought they were messengers of the gods. They came, they weren't predictable. Eclipses were predictable. Eclipses of the sun happen regularly, and people used that in some ways to make power. Comets were not predictable at all. And comets are leftover material from the birth of the solar system. They contain unaltered material from 4.5 billion years ago, when the solar system was put together. And that's really important, because when the solar system was young, the Earth was very hot. The Earth was too hot to have liquid water on the surface and to have organic molecules on the surface. So one of the big questions is, where did the water and organic molecules that we're all made of, where did it come from? And one of the possibilities is that about 500 million years later, when the Earth had cooled down, comets and asteroids hit the Earth, lots of them, and we know this happened. Did they bring water to the Earth? Did they bring organic molecules to the Earth? So this is, by studying comets, you understand the history of the solar system, how it was put together, because these comets formed in the early solar system. But you can also learn about what it means to be a human being. Were we made of stuff from comets? And at this point, I'm going to show you a film that we made in 2014 to try to bring this message across to the general public. We wanted to excite people about Rosetta. We wanted to explain this story about life, where did water come from. But we also wanted to do something a little sneaky. We wanted to tell people that what we were trying to do was incredibly difficult. To put a lander onto a comet. Nobody's ever done this before. How challenging was that? It was incredibly risky. And in fact, that's more or less everything we do in space science. We don't do boring things. We do things nobody's ever done before. And every time we do it, we're challenging, we're pushing the limits. And the one thing you need when you get into space, you've got to believe you're going to do it. And there's one word you need, and that's the title of this film, and that word is ambition.
Enough. Walk with me. Perhaps we should find you something a little less challenging.
I don't understand. I planned everything. Let me do it again.
Once upon a time.
Really?
This is a good one, I promise.
What is the key to life on Earth?
Water.
Water.
For a long time, the origins of water, and indeed life on our home planet, remained an absolute mystery. So we began searching for answers beyond Earth. Where could all this water have come from? In time, we turned to comets. 1 trillion celestial balls of ice, dust, complex molecules left over from the birth of our solar system, once thought of as messengers of doom and destruction, and yet so enchanting that we were to catch one. A staggeringly ambitious plan.
Are you talking about the Rosetta mission?
Throw me the probe. We harnessed whole planets and their gravity to chase down the comet. So many things could have gone wrong. A failure at launch, an error in the calculations, collisions, so many unknowns. With the technology we had back then, we may as well have been shooting from a slingshot. And tell me, what was it all for?
Knowledge.
Yes, but we also wanted to show what was possible.
I know all this from the archives. There were bigger missions after.
Yes, it was the first one to catch a comet. Ambition. Stubbornness. Nothing has changed. We fall, we pick ourselves up again, and we adapt. I was watching you earlier. You actually did everything right. I destroyed your rock. I needed to see how you would react. You're ready. Reset. Nicely done. Let's begin.
So do you have any Game of Thrones fans in the room? Anybody spot the 2 Game of Thrones actors? Yes, everybody Littlefinger, I hope you all spotted, but anybody tell me who the other actor, the actress was? Yes, somebody back there? No? Lyanna Stark from the last episode in the last series? It won't mean anything to you if you're not a Game of Thrones fan, but that was Aisling Franciosi and Aidan Gillen. Now, it grabbed a lot of attention, that film, and it really helped us kind of get the message out. But of course, in the European Space Agency, we're in the business of turning science fiction into science fact. So this is the real Rosetta, built between 1994 and 2003. It's roughly 32 meters across. It's the size of an Airbus A320, the wingspan. And in the middle is the Rosetta spacecraft with the Philae lander on the side. So this is roughly 3 meters by 3 meters. All the scientific instruments are on the top, and it's the powerful machine. Philae is much smaller, about the size of a big dishwasher, weighs 100 kilos, and has the small instruments to go down to the surface. So, where were we going? Well, this is the place we went to, and we are today. This is a comet called 67P Churyumov-Gerasimenko. and that is named after the two astronomers that discovered it, which is why I don't like it ever being called Chury, because two people discovered it, not just one. So you have to learn to say Churyumov-Gerasimenko, and that's as good as my Russian gets, I'm afraid. It was discovered in 1969. At its furthest distance from the Sun, it's out beyond the orbit of Jupiter, and at its closest distance, it's between Mars and Earth. Now, to get there, you launch a spacecraft on a big rocket. You get your biggest rocket, because you want to start from Earth and get on this orbit, and that's really hard. To get that energy to get onto that elliptical orbit takes a lot. So this is the launch, 2004. That rocket alone was not powerful enough to give us the energy we needed. So we did something else, and it was actually mentioned in the film. Now, the translator, don't even try. This is the entire mission in 27 seconds. You're not going to translate this. So, we launched in March 2004. 1 year later, we came back to the Earth, did a gravity assist. We went to Mars 2 years later, another gravity assist. Come back to the Earth a second time, go past an asteroid because you can. Come back to the Earth a third time, fly past another asteroid, go into hibernation, wake up 2.5 years later, start getting close to the comet, take pictures, work out where you're going to land, put the lander down, do science, get close to the Sun, end of mission. So that's the whole mission in 27 seconds. What we did each time we went past a planet, the Earth 3 times and Mars once, was to get more energy. We stole energy from the planets to fling us forward at high speed. So we managed to get onto this trajectory. I said we went to sleep here for 2.5 years when we were far from the Sun. We didn't have enough energy to run the whole system properly, so we turned it off. We turned off everything except some heaters to keep the fuel warm and an alarm clock to wake us up. And in January 2014, 18 minutes after the alarm clock was supposed to go off, this was the scene at our control center. Some very worried people, because of course if it didn't wake up, we had no mission at all. We could not connect with the spacecraft. It had to wake up on its own. 1 minute later, we got the signals through the ground stations, and that was the room. That was the reaction, as you can imagine. So some incredibly happy people. And over the next few months, we went to the comet, and we were expecting a fairly boring, fairly smooth object based on previous missions to comets. And that wasn't what we arrived at all. We arrived at an amazingly structured object, craters and structures and strata, and two parts to it, a head and a body. You know, this wasn't expected at all. So for the scientists, it was an amazing discovery because there was so much to look at. The engineers hated this because they had to fly around an object which wasn't spherical. And also, as you'll see in a few minutes, they had to try to find somewhere a 1 kilometer area, and this is 4 kilometers from here to here. They had to find a 1 kilometer area which was smooth to try and land on. There isn't one. So, interesting times for us in August 2014, and we started seeing a landscape which looks astonishing. There are cliffs, there are boulders, there are dust fields, but you have to remember this is not on the Earth. It's not made of rock, it's actually made of ice and dust mixed together. It's very light, it's much lighter than water. It would float half up above the water and half below. It's a very light object. There's no rivers, there's no erosion like on the Earth. So how did these cliffs form? How did these boulders get here? So this is what we've been studying for the last 2 years to try to understand this object. And we have regions on the back of the comet with big boulders. Well, how did that boulder get there? Where did it come from? And that boulder is about 20 meters tall. And just for scale, we called that boulder Cheops because it looks like a pyramid. This is the real Great Pyramid at Giza. So I made this image in 2014, and I realized that the European Space Agency couldn't release this image to the world because we have enough conspiracy theorists about aliens from space already. So it was released anonymously through the BBC, thankfully, but I did make it, yes. So we've been seeing these things, and we've been looking at the comet. We see places where boulders seem to stick on one direction, in other directions, because the gravity is not uniform. It's different everywhere you go. And the gravity is incredibly low. So this is one of my favorite places on 67P. It's a cliff 100 meters high from here to here. And everybody thinks the same thing when they see this picture, I hope. You think base jumping. Does everybody know what base jumping is? Standing at the top of a cliff and throwing yourself off? It would be the most boring base jump in history because the gravity on 67P is 100,000 times weaker than on the Earth. It would take you 20 minutes to get to the bottom. Incredibly boring. And then at the end, you would throw your parachute out, but there's no atmosphere, so your parachute wouldn't work. But that would be okay, because you only arrive at a speed of 25 centimeters a second, which is this fast. So you just get to the bottom and walk off the bottom. It's lovely. Now, but there's one thing you haven't realized yet. Now, if you've seen YouTube videos of base jumping, you stand at the edge and you push to avoid hitting the rocks here, right? Yeah, not on this comet, because if you jumped at 90 centimeters a second, you would reach escape velocity and go to infinity away from the comet. And to show you how easy that is, let's see, I always look at my audience. Are you ready? Are you ready for some exercise? Come on. If you stand up, I'm going to teach you how to jump off a comet. So if you all stand up, those of you who can. Because to reach 90 centimeters a second, you have to be able to jump 4 centimeters. That's all. If you can get to 4 centimeters, that's 90 centimeters a second. Now, I always say, if there are any Australians in the room, no 8 centimeters, no overachievement, because it doesn't matter. This is already going to take you to infinity. You can't go beyond infinity, okay? So we're going to do it together. No, we have to do it. We have to jump now. 4 centimeters, we do it together. 3, 2, 1, go! So now you know how to jump off a comet. That's good. Now, this comet is an amazing object. It has 2 pieces to it, and we're trying to understand, is that 2 comets joined together? Is that just one comet? We think it's 2 comets which collided in the early solar system. Our studies have given us strong clues about that. The Ambition film talked about water. It turns out the water in 67P is quite different to the water on the Earth. So at least this kind of comet, this is this point here, this is the Earth's water. 67P is up here. It's got too much deuterium in the water. So water on the Earth probably didn't come from comets in the end. Maybe came from asteroids, which are much drier, but if you get hit by enough, that's okay. But what it does contain are amino acids. This is glycine, and glycine is something which appears in proteins, which is the building blocks of DNA. And it also has phosphorus, and phosphorus is a very important element in DNA as well. So these comets can actually deliver the material needed. So I'm going to give 2 models out so you can get familiar. This is not the real size, as you might imagine. And it is that color, it's very black. Now I see that Miguel is standing up. That probably tells me he wants me to stop soon, but he's out of luck, at least for 5 minutes. What we had to do, of course, was land on the comet. This is what the comet looked like in September 2014, and comets throw out lots of material, and we wanted to get down to the surface before it got too active. This is one of the last pictures taken by Philae, the lander, of Rosetta, with a comet in the background. You don't see that every day. And we had to pick a place 1 kilometer across because Philae was just going to be thrown at the comet and it wasn't going to guide beyond that. It was just going to throw it at the right place. And we chose 10 places originally, and then we came down to the last 5. Each one of these is 1 kilometer across. And we ended up choosing this one, and I'm going to blow it up a bit. This is the area we chose to land, and that's 1 kilometer. We were going to land somewhere in that. We aimed at the middle, and in fact, we ended up here, very close. But you could see how dangerous it was. It was going to be risky. The comet was not smooth. This was always going to be difficult. So, if you're an astronaut, this is easy. You just do this.
Got it. Admittedly, it's translating really slow, but at least we hit our comet.
So this is Alex Gerst on the International Space Station. He took about 200 goes to make that work. For us, it was a little bit more difficult. This is what we had to do to get ready to launch the lander at this point here. And then it went down to the surface on its own. These are the last pictures taken of Philae looking back at Rosetta. These are the pictures taken by Rosetta as Philae went down to the surface, getting further away. And then we saw it traveling across down towards the surface. These are 3 pictures put together. There aren't 3 landers, there's only one. But over a period of 10 minutes, we saw it. And then this is the final 60 seconds of the descent. This is exactly what Philae saw at exactly the right speed. So it was incredibly slow at walking pace, moving down 60 meters. And it's worth looking at this and thinking, human beings can be remarkably stupid, unbelievably stupid. And I come from a country that's just done something remarkably stupid. I'm not going to say what it is, but you probably know. And yet occasionally we can be brilliant. Doing this 500 million kilometers away from the Earth has taken international collaboration through Europe, through the world. This is what working together can do. So that was the last image taken, 10 seconds before we touched down on the surface. This is the reaction, same people again, you recognize the faces, absolute jubilation. This is where we touched down. That's the spot there. Here are the 3 marks made by the lander. Now the clever amongst you will realize there's something missing from this picture. There is no lander in the picture, and that's because the lander is over there. The lander bounced, we all know this. The lander didn't secure itself to the surface, so it didn't catch the data, it didn't catch the surface, and it flew for a further 2 hours, bouncing across the head of the comet, hitting a wall, and then ending up here in a very dark location. So it operated perfectly for 3 days on its main battery, but there was not enough sunlight there to charge the other battery to have it continue doing science. This is the location where it touched down. And this is a raw piece of material of that comet. It looks like a rock, but it isn't. It's made of ice and dust fused together. And we've investigated that. And Miguel is going to bear with me because I'm in a Spanish audience. I'm going to summarize a lot of what the mission had done until that point in a video in Spanish.
Ha pasado un año desde la llegada de Rosetta a su nuevo hogar, el cometa 67P Churyumov-Gerasimenko. Rosetta ha estado muy ocupada todo este tiempo y también su módulo de aterrizaje Philae enviado a la superficie del cometa. El aterrizaje no salió exactamente según lo planeado, pero Philae se las arregló para tomar sus primeros datos en la superficie del cometa antes de quedarse sin batería y caer en un largo y profundo sueño. Rosetta siguió estudiando el cometa, descubriendo nuevas y maravillosas cosas a medida que lo acompañaba en su viaje por el sistema solar. El cometa mide 4 kilómetros de ancho y Rosetta ha calculado su masa a partir de la gravedad que ejerce sobre ella, 10.000 millones de toneladas. El cometa parecía una roca gigante, pero estaba hecho de algo mucho más ligero, tanto que incluso flotaría en el agua. A medida que el cometa se acercaba al Sol, Rosetta veía aumentar su actividad. Rosetta recogió muestras del gas y el polvo que el cometa lanzaba al espacio para averiguar su composición y en qué parte del sistema solar se formó. Una de las principales preguntas que los científicos querían responder era de dónde viene el agua de la Tierra y si la hubieran traído cometas y asteroides hace miles de millones de años. A Rosetta le sorprendió descubrir que el vapor de agua que sale de su cometa tiene un sabor distinto del de los océanos en la Tierra. ¿Cómo afectaría este hecho a las teorías sobre evolución del sistema solar?, se preguntaban los científicos. También había otros muchos tipos de gases. Olía a una extraña mezcla de huevos podridos, establo de caballo y mazapán. Rosetta recolectó también miles y miles de granos de polvo pequeños y grandes. Algunos parecían muy esponjosos, como un diente de león. Con el paso de los días, el cometa se volvía más y más espectacular. Rosetta sobrevoló muy cerca del cometa para verlo mejor, pero se encontró rodeada de muchísimo polvo. No fue tan peligroso como cuando su abuelo Giotto sobrevoló el cometa Halley a gran velocidad hace muchos años, pero Rosetta se desorientó y estuvo a punto de perderse, así que decidió proseguir su viaje desde una distancia más segura. Rosetta empezó a ver cómo cambiaba la superficie del cometa a medida que se aproximaba al Sol. Vio manchas de hielo y pozos expulsando chorros de polvo. El cometa se volvía más activo, pero aún estaba bastante frío en la superficie. Rosetta midió temperaturas de unos 100 grados centígrados bajo cero, y el interior estaba aún más frío. Consciente del frío, Rosetta se preocupaba por Philae, que llevaba durmiendo varios meses. Ni siquiera sabía exactamente dónde habría aterrizado por fin Philae, pero se preguntaba si tendría suficiente luz solar para recargar sus baterías. Entonces, un sábado de junio, Rosetta recibió una llamada. Era Philae. Había despertado. Enseguida se lo dijo a todo el mundo. Rosetta quería decirle a Philae todo lo que había pasado durante su sueño y sus emocionantes descubrimientos sobre el cometa, pero la conexión no era muy buena. Era muy frustrante. Rosetta tuvo que desplazarse de un sitio a otro buscando una mejor conexión. Philae esperaba volver a hacer pronto experimentos sobre la superficie del cometa, mientras Rosetta lo estudiaba a distancia. A medida que el cometa llegaba al punto de su órbita más próximo al Sol, crecían las ganas de Rosetta y Philae por vivir un acontecimiento único y por presenciar qué le ocurriría al cometa a lo largo del próximo año cuando se alejaran hacia las afueras del sistema solar.
So that was the status last summer as we were at perihelion. We did not know where Philae was. Of course, I can report to you that we do now know. Just a week ago, we found Philae. If you can't spot it in that picture, there it is. There's Philae, sitting on the comet, as it has been for more than a year and a half. These were the last possible chances to take images to find it, and we did. So we're extremely happy that we did, because we're nearly at the end of the mission now. The comet got very active, and on the day closest to the sun, in fact, we were a few hundred kilometers away, and we suddenly saw things like this, big jets of material bursting out from the hot comet. It was a good place to be far away from. But of course, in the meantime, the comet has moved out further away from the sun. It's cooled down. We're now taking pictures like this. This is from 75 kilometers away. We're seeing how the comet has changed during the time close to the sun, and we're comparing before and after to understand how comets evolve. And here's one of the closest pictures we've taken. This is just 4 kilometers from the surface, and this is about 100 meters across. And if we put something to scale in there, it would look like that. So that's Rosetta. Now, we've done all this complicated work for years, and you think we've just been sitting next to the comet. Let me show you what we've been doing for the last 2 years. This is the whole mission with its flying around the comet. I've speeded it up just a little bit. And this is all for science. This is to do different science from different distances, investigate different regions of the comet and its tail. So we've been flying around very complicated trajectories, and we've been using fuel to do that, and so we're running out of fuel. We're also moving far out into the outer solar system. There's little power again, and so we are reaching a decision point. Do we turn the mission back to hibernation after this full mission from 2004? This was 2015. Do we turn the spacecraft off and wait 3 years till it comes back? We don't think it'll work a second time. We're going further away from the sun than ever before, and the spacecraft is old. So we're going to do something different. We're going to land on the comet next week on Friday, and we're going to do science all the way down to this point on the surface There's a big pit, a big hole in the ground. We're going to take amazing pictures inside that, where we think we'll see inside the comet, because that's about 130 meters across, 50 meters deep. And we think inside there we'll be able to see what the comet is made of on the inside. So this is what the final descent will look like next Friday. And when we hit the surface, Rosetta will be turned off forever. Partly because the big dish will not point to Earth anymore. As soon as we're on the surface, it won't be able to point to the Earth. And we also have to turn it off because we don't want to pollute radio frequencies. So when we touch down at 12:40 CEST next week, that will be the end of an astonishing journey. I told you I'd get emotional. And so I just want to leave you with this final slide, because we have done an amazing thing, and I just want to leave you some words to describe how astonishing it is to have been a privileged part of this. And when this is finished, I take your questions. Thank you.
Even the greatest of journeys must come to an end. But most important is to realize your ambitions, to see and do wondrous things, and to light a path for those who will follow after.
Thank you very much.